Dear students, it is clear from our previous analysis that OLS estimators are functions of sample values. In the two-variable model, in deviation form, beta 2 hat is sigma xi yi by sigma xi square, and beta 1 hat is y bar minus beta 2 hat x bar. So as functions of sample values, the value of OLS estimators vary from sample to sample. The value of OLS estimators vary from sample to sample. So we require a measure of the precision of OLS estimators. As the value of the estimators vary from sample to sample, we require a measure of the precision of OLS estimators. The measure of the precision of the OLS estimators is given by the standard error. Standard error of estimators. And standard error is nothing but the standard deviation of the sampling distribution of the estimator. Standard error is nothing but the standard deviation of the sampling distribution of the estimator. The sampling distribution of the estimator is nothing but the probability distribution of the estimator. The sampling distribution of the estimator is nothing but the probability distribution of the estimator. So our next concern is derivation of the standard error of estimators beta 1 hat and beta 2 hat. Derivation of the standard error is required as a measure of the precision of the estimator. Not only that, standard error of the estimator is also required for hypothesis testing. Because for hypothesis testing we use the sampling distribution, and the test statistics derived from the sampling distribution. So we can use a test statistics or an estimator for hypothesis testing if and only if the standard error of the estimator is known. So now next concern is derivation of the standard error of beta 1 hat and beta 2 hat. And in our discussion, we will derive only the mean and standard error of beta 2 hat and mean and standard error of beta 1 hat will be simply stated. So let us first derive the mean and standard error of beta 2 hat. Now, we have shown that beta 2 hat is equal to sigma xi yi by sigma xi square. This can be written as sigma xi yi by sigma xi square. This we have derived earlier. Yi is capital letter yi, xi is deviation from the mean value, sigma xi yi by sigma xi square. This can also be written as sigma ki yi, where ki is equal to xi by sigma xi square. Ki is xi by sigma xi square. Now, as beta 2 hat is equal to sigma ki yi, we can expand it as equal to k1 y1 plus k2 y2 plus etc. kn yn. So, beta 2 hat is a linear function of y1, y2, etc. yn with the k1, k2, etc. kn serving as the weights. So, we can say that beta 2 hat is a linear estimator. Beta 2 hat is a linear estimator with the ki equal to xi by sigma xi square serving as the weights. Now, this weight ki is very important in econometrics. So, let us see what are the properties of the weight ki. The first property is that since xi is assumed to be fixed in repeated samples, xi is assumed to be non-stochastic. So, as ki is equal to xi by sigma xi square, ki is also non-stochastic. Ki is also non-stochastic because it is assumed that xi is fixed in repeated samples. So naturally, it remains constant from sample to sample. So it is non-stochastic. So ki being a function of xi is also non-stochastic, like xi. The second one is sigma ki equal to sigma of xi by sigma xi square equal to sigma xi by sigma xi square equal to 0, because in the numerator sigma xi is equal to xi minus x bar equal to 0. So the second property is sigma ki is equal to 0. Sigma ki is equal to 0. Third, sigma ki square is equal to sigma of xi by sigma xi square whole square equal to sigma xi square divided by sigma xi square whole square equal to 1 by sigma xi square. So sigma ki square is equal to 1 by sigma xi square. And a fourth one is sigma ki xi equal to sigma ki xi. The reason is sigma ki xi is xi minus x bar equal to sigma ki xi minus x bar into sigma ki, and sigma ki is 0. So is equal to sigma ki capital letter xi. Sigma ki small letter xi is equal to sigma ki capital letter xi is equal to sigma xi by sigma xi square. This is equal to sigma xi minus x bar into xi by sigma xi minus x bar square. Sigma xi minus x bar square. This can be written as sigma xi square minus x bar into sigma xi divided by a derivation of this, an expansion of this we have considered earlier, that is sigma xi square minus x bar into sigma xi equal to 1. So remember these properties of ki. Ki is non-stochastic. Sigma ki is equal to 0. Sigma ki square is 1 by sigma xi square. Sigma ki xi is equal to sigma ki capital letter xi is equal to 1. Now, given this, we can derive the standard error of beta 2 hat and also beta 1 hat. Now, so since beta 2 hat is equal to sigma ki yi, beta 2 hat is a linear estimator with the ki serving as the weights. It is a small sample property of an estimator we have discussed. Now, we substitute for yi from the PRF. This sigma ki yi is equal to sigma ki into beta 1 plus beta 2 xi plus ui, that is yi, is equal to beta 1 sigma ki plus beta 2 sigma ki xi plus sigma ki ui, that is beta 2 hat is equal to beta 1 sigma ki plus beta 2 sigma ki capital Xi plus sigma ki ui. And as we have derived already, sigma ki is 0, this is equal to 1. So beta 2 hat is equal to beta 2 plus sigma ki ui. It also follows that beta 2 hat minus beta 2 is equal to sigma ki ui. Beta 2 hat minus beta 2 is equal to sigma ki ui. Now beta 2 hat is equal to beta 2 plus sigma ki ui, and expected beta 2 hat is equal to, since beta 2 is a constant, its expectation is beta 2 plus, when we take the expectation of sigma ki ui, as ki is assumed to be a constant, it becomes sigma ki expected ui, and expected ui by assumption is equal to 0. So beta 2 hat is equal to beta 2. And this shows that beta 2 hat is an unbiased estimator of beta 2. Beta 2 hat is an unbiased estimator of beta 2. It is actually the unbiasedness property. And remember this, unbiasedness property will be satisfied if and only if xi and ui are uncorrelated. That is, the second assumption, covariance xi ui is equal to 0. Never think that expected ui 0. Actually, we take it as expected ui because ki is assumed to be fixed in repeated samples. As we have seen, expected value of ax is equal to a times expected x. Otherwise, we cannot write it like that. So, as I told you earlier, xi is assumed to be fixed in repeated samples is a simplification used at an introductory level to derive the results easily. Otherwise, we have to go for if a and b are variables, then expected ax is expected a into expected x, provided that a and x are uncorrelated on the assumption that a is also a variable. So, but if we assume that x is fixed in repeated samples, this can easily be written like this. So we have expected beta 2 hat is equal to beta 2. Beta 2 hat is, so expected beta 2 hat is equal to beta 2. And similarly, we can prove that expected beta 1 hat is equal to beta 1. This is given in all the books, it's not required. We need to prove only expected beta 2 hat, the other is automatically satisfied. Now let us see the variance of beta 2 hat. Now, variance of beta 2 hat given as expected value of beta 2 hat minus expected beta 2 hat. Since expected beta 2 hat is equal to beta 2 is equal to expected value of square is there, the standard formula for variance. Expected value of beta 2 hat minus beta 2 the whole square. Remember, this is the formula for variance. And we have already written that beta 2 hat minus beta 2 is sigma ki ui. So this is written as expected value of sigma ki ui the whole square. Sigma ki ui the whole square. This can be written as expected value of, we have while discussing about the properties of summation operator, we have expanded the term sigma xi the whole square as x1 square plus x2 square plus xn square plus 2 x1 x2 etc like that. So expanding this, you will get it as k1 square u1 square plus k2 square u2 square plus etc kn square un square plus 2 k1 k2 u1 u2 plus etc plus 2 kn minus 1 kn u n minus 1 un. That is the expansion. All the squares cross products. Now we take the expectations operator inside. This is equal to k1 square expected u1 square plus k2 square expected u2 square plus etc kn square expected un square plus 2 k1 k2 expected u1 u2 plus etc 2 kn minus 1 kn expected u n minus 1 un n minus 1 un. Now you can see that this is equal to k1 square. Now expected ui square is equal to sigma square, homoscedasticity assumption. So expected u1 square sigma square, k2 square sigma square plus etc kn square sigma square. Then expected ui uj 0, no autocorrelation. So all these terms becomes 0 when expectation is taken. So remember this. From this you will get to this result if and only if there is no heteroscedasticity and autocorrelation. So this is derived from the assumption of homoscedasticity and no autocorrelation. Remember this. This is derived by assuming that covariance xi ui is equal to 0. So the derivation of the formula of variances, expected value etc. critically depends on the assumptions of classical linear regression model because these assumptions are used. Now this is equal to, since sigma square is a constant, we write it as sigma square into sigma ki square. And as we have considered the property of sigma square, this is equal to sigma square by, since sigma xi square is 1 by sigma ki square is 1 by sigma xi square divided by sigma xi square. This is variance of beta 2 hat. The variance of beta 2 hat is sigma square by sigma xi square. And the square root of the variance. The square root of the variance of beta 2 hat is known as the standard error of beta 2 hat. The positive square root of the variance of beta 2 hat is known as the standard error of beta 2 hat. We write it as standard error of beta 2 hat as equal to the positive square root of, that is root of sigma square, sigma by root of sigma xi square. And this quantity is used for hypothesis testing, for the derivation of z, t, etc. So keep this always in mind. Standard error of beta 2 hat is sigma by root of sigma xi square. Sigma by root of sigma xi square. So variance of beta 2 hat is equal to sigma square by sigma xi square. Variance of, and its positive square root is the standard error of, and it is nothing but the standard deviation of the sampling distribution of beta 2 hat. Because beta 2 hat is an estimator, it has a sampling distribution, and it is a random variable from our previous analysis. Similarly, without a proof, we can show that variance of beta 1 hat is equal to sigma square into sigma xi square divided by n into sigma xi square. Variance of beta 1 hat is equal to sigma square into sigma xi square divided by n into sigma xi square. This is capital letter X, this is small letter x. So this is deviation from mean value. This is in terms of original value of x. And standard error of beta 1 hat is equal to, you can write it as root of sigma xi square by n into sigma xi square into sigma. This term in the roots and sigma outside the roots. Now, this is variance of beta 1 hat and it's a standard error. This is variance of beta 2 hat and it's a standard error. These quantities are used as a measure of the precision of the estimator. Not only that, these quantities are used for hypothesis testing. Then when we consider prediction later, we will use the variance of beta 1 hat from here. 1 hat as equal to sigma square into 1 by n plus x bar square into 1 by sigma xi square is equal to sigma square into sigma xi square plus n into x bar square by n into sigma xi square. When we take a LCM, n into sigma xi square can be written as sigma square into, the expansion of sigma xi square is sigma xi square minus n into x bar square plus n into x bar square divided by n into sigma xi square is equal to sigma square into sigma xi square in the numerator, in the denominator n into sigma xi square. This is the formula. Its actual derivation is not considered here because it is not very important. We need to consider this only, and when we consider prediction using simple linear regression model, we will start from here. That I will explain later. Now, consider these formulas of variance and also standard errors. You will immediately feel that in this formula, Sigma xi square is known once we have the sample. Here also sigma xi square is known, sigma xi square is known, n is also known, sample size. What is unknown is sigma square. And sigma square is the variance of u, the stochastic error type, and u is unknown. So we cannot apply the formula of variances for hypothesis testing. So what we do in practice is we replace sigma square with its unbiased estimator. Sigma square is replaced with its unbiased estimator sigma hat square equal to sigma u hat I square by n minus 2. Sigma hat square is equal to sigma u hat I square by n minus 2. What I say is, for the practical application of the variance formulas, sigma square must be known. But the problem is, sigma square is always unknown. So we replace sigma square with its unbiased estimator sigma hat square, which is given as sigma u hat I square by n minus 2. As you can see, this is nothing but the sum of squares of residuals. N minus 2 is known as the degrees of freedom. The degrees of freedom. It is a concept which we have discussed in detail in the context of variance. For example, we have seen that s square is equal to sigma x minus x bar square by n minus 1, where n minus 1 is the degrees of freedom. As I told you, as deviations are taken from x bar, not all these deviations, all these variables are independent. If n minus 1 is known, the nth one is also known. Another interpretation is, since a quantity is estimated from the sample, a restriction was imposed on the sample, so we have only n minus 1 degrees of freedom in the deviations. Here, in the context of OLS, sigma u hat I square can be derived if and only if beta 1 hat and beta 2 hat are derived. So two restrictions are imposed on the data when two quantities are estimated from the data. Or as we have seen, sigma u hat I is equal to 0, sigma u hat I xi is equal to 0. These are the two restrictions imposed on the data. So two restrictions imposed on the data. So we have n minus 2 degrees of freedom. As I told you earlier, the degrees of freedom is in general is known as n minus number of parameters estimated, n minus k. And as I told you also, remember this, degrees of freedom is an adjustment to make an estimator unbiased. Now, sigma hat square is the unbiased estimator of sigma square. So naturally, we want expected value of sigma hat square equal to sigma square. Expected sigma hat square equal to sigma square. If you take an expectation of sigma u hat I square, you will get it as equal to n minus 2 into sigma square. If you take an expectation of sigma u hat I square, you will get it as n minus 2 into sigma square. A proof of this will be considered when we consider the k variable model. Anyway, for the time being, remember that the expectation of the numerator is n minus 2 into sigma square. So if you divide here with n minus 2, here also n minus 2, so it becomes sigma square. So division by n minus 2 make the estimator of sigma square, that is sigma hat square, an unbiased estimator. So in the formula of variance of beta 2 hat, And also in the formula of the variance of beta 1 hat, sigma square is replaced by sigma u hat I square by n minus 2. These adjustments make these formulas operational. And also remember this, we divide this quantity with n minus 2 to make this estimator an unbiased estimator. N minus 2 is known as the degrees of freedom, is nothing but the number of independent variables minus less the number of independent constraints imposed on these variables. And one constraint is imposed when only one quantity is estimated. Two constraints are imposed when two quantities are estimated. K constraints are imposed when K quantities are estimated, like that. Now one more point is, the question is, how do we calculate sigma u hat I square here? Now, actually sigma u hat I square is equal to sigma of yi minus beta 1 hat minus beta 2 hat xi the whole square. Once beta 1 hat and beta 2 hat are calculated, then it is easy to calculate sigma u hat I square. But in practice, we calculate it differently. We know that yi is equal to y hat I plus u hat I, and in deviation form yi is equal to y hat I plus u hat I. And sigma yi square is equal to sigma y hat I square plus sigma u hat I square plus 2 sigma y hat I u hat I. Sigma yi square is equal to sigma y hat I square plus sigma u hat I plus 2 sigma y hat I u hat I. Sigma yi square. And as we have proved in the context of numerical properties, this quantity is 0. So sigma yi square is equal to sigma y hat I square plus sigma u hat I square. Now it follows that sigma u hat I square is equal to sigma yi square minus sigma y hat I square. Sigma yi square minus sigma y hat I square. And that since y hat I is equal to beta 2 hat xi, sigma y hat I square is equal to beta 2 hat square into sigma xi square. So sigma u hat I square is equal to sigma yi square minus beta 2 hat square into sigma xi square. This is the formula which we use to calculate sigma u hat I square. yi square minus beta 2 hat sigma xi square. Beta 2 hat square sigma xi square. The formula used for calculating sigma u hat I square. In the age of softwares, computer, etc., such calculations are not required. Software packages will give the estimates automatically, and we will discuss the most popular softwares used in econometrics at a later class. Anyway, then one more point is the quantity, that is sigma hat, is root of sigma u hat I square by n minus 2 is known as the standard error of the estimates. The standard error of the estimates. Sigma hat equal to root of sigma u hat I square by n minus 2 is known as the standard error of estimate. And standard error of estimate, also known as standard error of regression. And it is nothing but the standard deviation of y around the estimated regression line. It is nothing but the standard deviation of y around the estimated regression line, and it is often considered as a measure of goodness of fit of the sample regression line to the sample data. That is sigma u hat I square by n minus 2, standard error of the estimate. It is nothing but the standard deviation of y values around the sample regression line, the estimated regression line, often used as a summary measure of the goodness of fit of the sample regression line to the sample data. Now, from the definition of the variances and standard errors of the estimates, consider these points. Variance of beta 2 hat is equal to sigma square by sigma xi square. Variance of beta 1 hat is equal to n into sigma xi square by sigma square into sigma xi square by n into sigma xi square. There are some points above that we discuss with regard to these formulas. Remember this. Consider the slope coefficient beta 2 hat. In this case, variance of beta hat 2 is directly proportional to sigma square. As the variance of u increases or the variance of y increases, variance of beta 2 hat also increases. It is inversely proportional to sigma xi square. And what is this sigma xi square? This quantity is sigma xi minus x bar square. Remember this, if all the x values are equal to x bar, that is, there is no variability in x, this becomes 0. And the variance of beta 2 hat become infinite. 0 here means variance is infinite. So if you have a sample with a low variability in x, then the variance of the estimator will be very high. Precision of the estimator will be low. On the other hand, if you have a sample with a high variability in x, variability in x is very high, then this quantity will be low and the variance of beta 2 hat will be low. So the message is, if you have two data sets with different values of x, then always select the set with the high variability in x. As the variability in x increases, precision of the estimator also increases. Variance of beta 1 hat depends on these quantities, not very important for our purpose because it is the intercept. Intercept is not always meaningful. So remember this, we have proved that OLS estimators are linear, OLS estimators are unbiased. And though we have not stated this explicitly, we have derived the mean and variances of OLS estimators. And this is very important for hypothesis testing. That I will discuss when we consider hypothesis testing in a future session.